All right, let's look at some of the wave properties of light. So we've talked about light as electromagnetic radiation, and now we're going to talk about how we know basically that that functions like a wave. So some foundational facts just to know. All electromagnetic radiation travels at the same speed, and that is the speed of light. I guess I don't actually need that. And in a vacuum, this speed of light is about 3 times, that is just real messy. So let's just rewrite it up here. It's about 3 times 10 to the 8th meters per second in a vacuum. If it's traveling through something else, it will be slower than that. But in a vacuum, so in space, all light, all waves that are in the electromagnetic spectrum will travel at the speed of light. The brightness of light, so how bright a light is related to its amplitude. So much like with sound, where sound, the loudness is related to amplitude, with light, the brightness is related to amplitude. And just as a side note, as light spreads out, it obeys something we call an inverse square law. Which means that as you get twice as far away, you square that and invert it, and that tells you how bright it is. So light that's twice as far away is 1/4 as bright. Light that's 3 times farther away is 1/9 as bright. And this is because light spreads out in all directions. So if you have your light source and you imagine drawing bigger and bigger circles, well, the light's going to be on that entire surface of that sphere. So if the radius, if the distance is twice as far, the light has to spread out over 4 times as much area, so it becomes less bright accordingly. And then the energy of light is related to the frequency. And we can't, in this case, say it's related to wavelength, even though those are closely related, because the speed of light can change if you're not in a vacuum. But the energy is, you don't need to know this equation, but I'll point it out here. It's E equals HF. Don't worry what H is, it's a constant. But it's literally the frequency times this constant that gives you the energy. If you had wavelength, you can put wavelength into the equation, but then it's got to be E equals H, I'm going to make sure I do this right, yeah, C over wavelength. So it is sort of related, but again, we really want to focus on thinking about it as frequency. And as you can see from that equation, higher frequency means more energy. And then, other than that, all the other standard wave properties apply. Interference, diffraction, refraction, etc. And we've got an extra slide in here, so we'll skip past that. Okay, there is something, this is technically a property of all waves, but we care about it most with light. And polarization refers to all the waves being aligned. I think that's a misspelling of align. I think it should be one L. But it's all aligned in the same direction. And this is useful to selectively block certain kinds or amounts of light. So this diagram right here is not what happens with light because of reasons that are technical that we can talk through if you care one-on-one, but it's a good illustration of the general idea. So if you imagine you've got a bunch of small thin openings, if you shake a rope, it's only gonna, like the wave is only gonna go through if it's going up and down. If the rope's going side to side or at an angle or something like that, the side to side motion is gonna, hit the wall and not go through. So then if you imagine having a bunch of these slits all next to each other, then only the quote-unquote up and down waves will go through. Any of the side-to-side waves will bounce back, or they'll be absorbed by these slits. And what this ends up doing, if you're just kind of outside in the, just random light from everywhere, and you've got sunglasses that are polarized, what they end up doing is they'll only let, because of the way this is, functionally they only let about half the light in. So that means it brings the light down, and there's less light hitting your eyes. It feels less bright because there's, less stuff happening. This is also how you can tell if sunglasses are polarized or not, is because you should be able, if you look on the outside, you should be able to see reflections, because a lot of the light is getting reflected back, anything that was going side to side. That being said, there are some sunglasses, well, actually any sunglasses that have sort of a mirrored finish, the more mirrored it is, the better it is at blocking light because it's reflecting it back. But not all sunglasses with like a mirrored finish are polarized. The other neat thing that will happen is if you've got, say, a reflective surface like water, when light hits it and bounces off, that will end up polarizing the light that comes off of it. So what this means is if you have sunglasses, and you can do this next time you're out and about, if you have polarized sunglasses and you look at, say, a glass wall on a building where it's hard to see in because of the reflection, or there's some water where lots of light is reflecting off so it's hard to see under the water, see like fish or something, if you take those polarized lenses and you twist them until they basically are blocking all the light that's reflecting off of the glass or reflecting off of the water, it will let you see very clearly through that glass or into that water. I'll try and see if I can get something set up in the classroom where we can test this and see this, but it's a really neat thing where you can see that polarization at play. Then we'll also mention diffraction briefly with light because we use it for measuring things. So we already know that with diffraction, waves will bend when passing through an opening. And the closer the size of the opening to the wavelength of the wave, the more bending or curved the wave will look. So if you look down at the bottom here, in the first example, there's a big difference between wavelength, between these peaks and the size of the opening. And so we see that for the most part it goes straight through, and there's a little bit of curving just at the edges, because it will always curve around the edges. And then when you get closer, then the wavelength, the curving on the edges, produces, we get a little more bendiness. And we get really close, when these are about the same size, we get lots of curvature. And I think I mentioned this before, but this also happens the opposite way, in a sense, of if you've got a really narrow opening. So imagine you've got an opening like this, but a really big wavelength, they will go through and be mostly straight. There will still be a little bit of curving, but it will mostly be straight, going straight out like that. So we only get this really big, intense bending when they're about close. And so we can use this to measure the wavelength of light. By seeing how much it bends going through a known opening. And there's special ways you do this, but basically, if you know the size of an opening and you shoot light through it, you can measure the bending of it and then determine, oh, they were this close, and therefore that's how big the wave is. It doesn't work exactly like this, but it's functionally, oh, the wavelength bent this much, so the wavelength should be twice the size of the slits, or half the size, or 3/4 of the size. Again, it's not exactly like that, but it's analogous to it. And then lastly, we look at refraction, and this occurs when light moves between different media. So if it moves from the air into the water, or the water into the air, or air into glass, etc., etc. And this, oh yeah, when it does that, the speed of light changes, and the light bends. And so the example is, you imagine you've got like a little toy car rolling on the sidewalk. And then if it's rolling, I drew this poorly, let's draw it again. So we've got the wheels. If it's rolling at an angle, when this wheel rolls off the sidewalk into the grass, it'll slow down. The front wheel is still on the sidewalk, so it'll travel faster, and we end up getting it to turn to some angle like this. And refraction is really important for what we'll do in our next unit, which is looking at optics and how we use lenses to focus and bend and deflect light and all sorts of things there. But that'll wrap us up here with the wave properties of light. Let me know if you have any questions, but otherwise, like I said, we'll close it here.